Okay, we have retained another interesting integral that was sent to me by Sid. We have here the integral from 1 to infinity of the floor of sine pi x over the floor of x times the ceiling of x dx. Okay, this one was pretty interesting. I was thinking back, and I think I've done one with something very similar to this, what we have in the denominator. And I know I've done something very similar to this, but I don't think I've ever done this problem with both this and this in the same integral. Now, to get started with this, we have the property that the floor function is basically going to round us down to the next highest integer, and the ceiling is going to kind of take us up to the next integer. And so oftentimes how we want to handle this is if we break up our integral so that the lower bound and the upper bound are just separated by 1, we're going to get a lot of simplification. So for this first integral, we'll just go from 1 to 2. What's going to happen is with all of our x values between 1 and 2, here the floor is going to round us down to the lower bound of 1. And then for the ceiling, that's going to round us up to the upper bound, and that's going to be just 2. So for our denominator, we just have 1 times 2. And now for what we have in the numerator, it's a little more complicated, but the pi is going to help us simplify it. So let's just look at a rough unit circle to see what's happening. Now if we look at what happens when x is 1 at the lower bound, we plug that in there. So if we look at what happens when our x values are between 1 and 2, when we plug it in as our input on the sine, it's going to be starting at like 1 pi, and our input's going to go all the way to the upper bound, or 2 pi, like this. So for sine pi of x, we're going to be looking at all these values here in quadrants 3 and 4. And so each of these values is going to be between 0 and minus 1. Technically at the endpoints, it's going to be 0, but in an integral, we don't really consider the actual endpoint. So we're going to be looking at everything below this, everything below 0. And so in every case, the floor is going to round us down to this bottom value, which is going to be minus 1. So the numerator here is just going to be minus 1, and this all reduces down to a constant. Then let's just do the same thing going on to the next one. We're going from 2 to 3. Same exact thing in the denominator. On the first one, the floor is going to round us down to the lower bound, 2. Ceiling is going to round us up to the upper bound, 3. Then when we look at what's happening in the numerator, our sine values are going to be from 2 pi here, and they're going to go to 3 pi. Of course, we're going around and around, so this value here takes on multiple values. So when we take the sine value between 2 pi and 3 pi, we're going to get all these values in here. So all of our values are going to be between 0 and 1. Technically, we're going to hit 1 at just this one point here, right? We're going to technically be at 1 there. But again, with an integral, we don't care what happens at just one point. So really, we're considering all values that are less than 1 and greater than 0. But in every case, the floor is going to round all these values down to 0. And so our numerator here is just going to be 0. And now, of course, we can keep going, but the thing is, it's just going to start repeating right here. So here we're going to be going, this is going to be 3 times 4. But then in the numerator, when we look at what happens between 3 pi and 4 pi, then we're back in the same scenario here. The floor is going to round everything down. This becomes a minus 1. So as it turns out, every time our lower bound is going to be even, like this one right here, we're going to get the same thing. We're going to get a 0 in the numerator. It's going to 0 at the whole integral. And so all these integrals are going away, and we just need to consider the ones with odd numbers as the lower bound. And now this thing's going all the way to infinity. That's our upper bound here, so it's just going to go on forever. But let's see what we can do to generalize this. So first of all, what I'm going to do, since the lower bound is always going to be odd, all the even cases get wiped out, I'm going to represent this lower bound as 2n plus 1. And so just adding 1, our upper bound becomes 2n plus 2. We're always going to have this minus 1 here in the numerator. And then for the denominator, it's just going to be the lower bound times the upper bound. So it's just going to be 2n plus 1 times 2n plus 2. And now when we integrate this, this is all going to be a constant with respect to x. So we can just bring this up front of the integral, and we're really just integrating 1. So if we do that, let's just call this constant value here a, just so I don't have to write it again. And then when we integrate, we're just getting, integrate 1, we get x, and we're just evaluating from 2n plus 1 to 2n plus 2. But when you evaluate that and you do 2n plus 2 minus 2n plus 1, this here all reduces to 1, and we just get back a. So at this point, because our bounds are always separated by just 1, we can just drop the integral. Everything is going to be just the constant value, and all we need to do is sum up all these constants. So what we can do is take this and put this into a series. I can write this as n equals 0 going to infinity of this thing, And just notice if you plug in a few terms here, like when n is 0, you're going to get this. When n is 1, you're going to get this one, and on forever. But now from here, this sum is a little difficult to deal with in this form right here. So what I want to do is break up this denominator. Now what you could do on this is partial fractions. I'm going to kind of skip a step. And what we can do is reduce it by replacing our -1 using this denominator to get cancellation. So I can do this, I can write this as 2n plus 1 minus 2n plus 2. Just notice the 2n's cancel, 1 minus 2 gets us back to -1. So we haven't changed it here. And now if we separate this into two fractions, in the first one, the 2n plus 1's are going to cancel, and we have 1 over 2n plus 2. And then in the second fraction, the 2n plus 2's cancel, and we get 1 over 2n plus 1. But now let's just write out a few terms to see what's happening here. I'm going to kind of go out of order. If I plug the 0 in here, we're going to get just -1 for the first term. I plug 0 in here, this is going to become plus 1/2. Then we plug 1 in. If we plug 1 in right here, we have -1/3, and then plus 1/4, and then -1/5. And you may recognize what we have here. This is just the alternating harmonic series. Or I should say it's the alternating harmonic series times -1, because the alternating harmonic series is supposed to start with 1. And then this has a well-known value, and so we could just put down the answer for this now and be done with it. But I think I want to go and put it back into series form and show how we calculate that value. So the way I can write this for the alternating harmonic series is we can write it as the sum from 1 to infinity, and it's just going to be -1 to the n plus 1 over n. But like I said, what we actually have is -1 times the alternating series, so we can just multiply by a -1 in front here. But then I'm going to actually just multiply that in, and so when I rewrite it, now we have the same base with the -1, so we could write this as -1 to the n plus 2. But that's going to be the same thing as -1 to the n, because when you have something with -1, it's just based on the parity. And so this is going to be the same thing as just -1 to the n. And then from here, what I want to do is I want to notice the similarity of this to something that just looks like x to the n over n. So if I call this over here our f of x value, then our goal that we want to find for the solution of this whole thing is going to be just f of -1. Coming over here, I'm going to just differentiate this. Using power rule in this, we're going to get n x to the n minus 1, but the n's are going to cancel, so this is just going to become x to the n minus 1 from 1 to infinity. But now let's just do an index change on this. If I add plus 1 to n right here, this is just going to become an n. But in order so we don't change it, we need to subtract 1 from right here, so this becomes n equal to 0. But now this right here, this is our formula for the geometric series. This is going to be the same thing as 1 over 1 minus x when the absolute value of x is less than 1. But now at this point, I just want to get this and get it back to f of x using what we have over here. And so what I can do is I'm just going to integrate here on both sides, because when we integrate f prime of x, we're going to get back to f of x. So what we're saying is that f of x is going to be the same thing as the integral of 1 over 1 minus x, and we're integrating with respect to x. When we do this, this is just going to be natural log absolute value 1 minus x, but then we need a minus sign to come out because of the minus on the x. We'll have it like minus natural log 1 minus x, and we'll have a plus c on there. Now from here, in order to deal with the plus c, what we can do is we can use a known value like f of 0. Coming back here, this is our f of x too. If you plug 0 in here, every term's 0, the whole thing's going to be 0. So we know that f of 0 is going to be 0. We'll plug it in here, minus natural log. We don't really need absolute value because for this to converge, our x values need to be between 0 and 1 here. So then plugging in 0, we're going to have just natural log of 1 plus c, but natural log of 1 is 0, so that means our c value equals 0. So for our f of x value, we can just drop the plus c because it's just going to be 0. And now at this point, we're ready to get this back to our goal, which is just f of minus 1, this thing over here. Now, one note on this, like I said before, the convergence here on this was that we needed absolute value of x less than 1. Well, this condition is true here, but when it's transformed, you need to check the endpoints. And so if you just do this really quick, you'll notice that x, it's going to diverge because then you have basically just 1 over n harmonic series that diverges by p series. But when you plug -1 in here, that actually converges by the alternating series test. And of course it converges because we're about to get a value for it. That's another reason. But if you did the test, you'd see that -1's okay here. So now to finish it off, we'll just use our formula here, and we need to evaluate for f of -1. So plugging in to get our f of -1 value, grab minus natural log, dropping parentheses 1 minus, plugging in -1. Minus times minus is plus. This is going to be minus natural log of 2. But I could bring this into the exponent and rewrite this if you like, or we could leave it, but I'll write it as natural log of 1/2, and that's it. Okay, there you have it. Interesting integral and an interesting series at the end to finish it off. Thanks everyone for watching. Have a good day.